person was Lothar Nordheim, who subsequently went to Duke. Was a very fine physicist. So I took these advanced physics courses, and Locke Horvitz tried to get me to come over and major in physics. And I checked this out and found out that physicists were having trouble getting a job. They had physicists around who had their PhDs and hadn't left yet. So I thought maybe I should look at, be careful about chemistry. So in looking at the situation in chemistry, the chemists were gaining jobs, having no difficulty getting good jobs at the time. So I decided to stay in chemistry but minor in physics as I had originally intended. So I worked with Professor R.F. Newton, who by the way is still alive, I think he's in his 90s, on a physical-chemical problem related to the heat capacity of supercooled glasses. I worked on glycerol glass, and it took me about 2 years, and I finished up in about February of 1937. Then to look for a job. There arrived on the campus one day a chemical engineer from Amoco, which Standard Oil Company of Indiana, which is now Amoco, and his name was Dr. George Lamb. And Indiana was looking for some physical chemists to do thermodynamic and kinetic work, and also work in catalysis. So I guess they decided I might be an interesting person, so they hired me, and I went to work there I think it was May 5th of 1937, which is almost 50 years ago. Now, next month it'll be 50 years. The thing that they, well, let me say that Standard of Indiana laboratories, the Whiting laboratories, had a lot of tradition there of the early research in petroleum, because that's where the thermal cracking work was done, and a lot of phase equilibria work was done by some of the workers. And some of these older people who had worked on these had retired, but they were still around. I met Dr. Humphreys, who was William Burton's assistant in developing the first successful thermal cracking process. And I chatted with him. He was a very cultured gentleman in his 80s, and came over to visit the labs occasionally. So there was a lot of tradition in high quality research there. So that really was an inspiration to me. But anyway, the first thing I did was spend about almost a year working up fairly good tables of thermodynamic properties of hydrocarbons. And I wrote a report on this and made this information available to the other chemists and engineers of the faculty, of the staff there. They weren't used to thinking in terms of thermodynamic equilibria, so as I learned more and more about hydrocarbon chemistry, I was able to assess possible kinds of reactions. So this gave me a big jump ahead of a lot of the people there, and so I started writing. I learned they had a patent system, and you're supposed to write these ideas up and submit them to the patent department. So I started doing that, and I did quite a bit of work predicting possible reactions for studying. And I can remember one of the reactions that I proposed was the addition of carbon monoxide and hydrogen to olefins. It just from thermodynamics, it was like a favorable reaction. But shortly after I'd written that up, literature appeared that reaction was being explored in Germany. So I ran into that occasionally, but I was able to do a lot of predictions for future research. Following this thermodynamic work, they put me on catalytic reforming, studying catalytic reforming. The idea was to raise the octane number of virgin light gasoline distillates. And so I worked with an inorganic chemist who had a PhD from Johns Hopkins. His name was Llewellyn Hurd, and we formed a team. Hurd made the catalyst. Through mutual discussion, we arrived at compositions we wanted to study, and we began to study catalytic reforming, which consisted of running gasoline hydrocarbons over various catalysts at various conditions to see what we could do to raise the octane number. This had been explored to some extent by other chemists, and there was a little literature in there, but not very much of significance. So we tried many different catalysts for this reaction, and we found that the reaction rate seemed to go down as a function of time, and after about half hour or an hour, the catalyst had lost most of its activity. And so what was the cause of that? And it was suspected that we were coating the catalyst with hydrocarbonaceous material, which we then proceeded to burn off and regenerate the catalyst. But we never could get very long cycles, and it didn't look very interesting. So we began to do some work on how to inhibit coke. We looked at pure compounds to see which were the coke formers, and we found out that one of the main coke formers was C5-naphthene, methylcyclopentane, and dimethylcyclopentane. And we published we did publish some of this early work in the Journal of the American Chemical Society, I think. I can remember giving them my first technical paper was in Cincinnati in April of 1940 at the ACS meeting in that town. And this coke continued to bother us. So I began to look at the equilibria involved, and I discovered that if we operated it, we could operate this reaction under hydrogen pressure, theoretically, and inhibit the formation of these olefin materials, particularly the cyclic olefins. The equilibria was at atmospheric pressure was about 20% dehydrogenation, and we thought that if we increase the hydrogen pressure, then we could cut down on that equilibrium and limit the concentration of the olefins. And looking at the thermodynamics of that showed that at about 500 pounds, if we ran at 500 pounds, we could limit the olefin concentration to less than 1%. And then we looked at what it might do, the hydrogen might do to other reactions, and found that looking at naphthenes dehydrogenating to aromatics, that was so favorable that even under hydrogen pressure we could get about 90% conversion, theoretically. So I remember how excited I was, and we made a presentation to the the company in the technical meetings to our bosses, and so it was decided to investigate, build some apparatus in which we could carry out these reactions under pressure. Well, about this time, we learned that other people were about maybe a little bit ahead of us and already learned that you could do this reaction under hydrogen pressure. But anyway, we subsequently built some small units and began to get some very interesting results as other people were getting. We were able to upgrade the octane number and get pretty good yields and get a reaction period up to 6 hours without regeneration. This by, you would make hydrogen in this process anyway, so you would just recycle some of the make hydrogen back to the system and control the total pressure with adding hydrogen. So the partial pressure of hydrogen was pretty high at 500 pounds, and it was sufficient to really control the coke formation. I wrote some disclosures on this, and whether we were first or not, I don't know. But anyway, Standard at the time was cooperating with Standard Oil in New Jersey and the M.W. Kellogg Company in this catalytic reforming. And whether we were first or not, I never knew. But anyway, Standard of Indiana did not proceed to get a patent on my disclosure. But we independently discovered the process, which was later called hydroforming. But as part of this work, I found that there were feedstocks that were high in methylcyclopentane.
Tamline, will you please call Kelly on extension 11? Tamline, please call Kelly on extension 11.
There were these feedstocks that were high, as much as 25% methylcyclopentane. By the way, we had to develop our own methods of analysis. And to do this work, I built the first high theoretical plate column at Standard of Indiana. I can remember I took off about 6 months to develop these better methods of analysis and develop this fractionating column, which would have 200 theoretical plates. So I could do things that hadn't been done before. And in analyzing these feedstocks, I discovered this methylcyclohexane, a high content of methylcyclohexane. And so I, in the catalytic reforming of this with hydroforming by then, reforming under hydrogen pressure, discovered I could make stoichiometric amounts of toluene out of the methylcyclohexane, or nearly stoichiometric amounts. So I had to develop methods of analysis to really get a fix on the amount of toluene, because toluene, by just distillation, you'd form azeotropes, and what you'd get over at the boiling point of toluene was not pure toluene. So I had to find out just how much pure toluene was there. And so I developed an analytical procedure for that. That took me some time. But anyway, I recorded all this in my notebooks. This is about early on in, I guess in the late 40s or early 41, when the U.S. was not in the World War II, and the World War II was really coming on strong, and it looked like the U.S. might get involved. So it was decided to investigate this further. And so I worked with some of the Standard Oil of engineers about this producing toluene. And one day they came down and got my notebook, my bound notebook, which I had recorded all my results about this and the method of analysis. I took that report away and I never saw it again. And I guess it became secret, and even though I had done the work, I probably would not have been able to take a look at it again. But anyway, following this, Standard of Indiana and cooperated with these other Standard Oil New Jersey and under Kellogg, and developed not only the catalytic reformer to upgrade gasoline, but to make chemicals, namely make toluene. And as a result of the work of this consortium, as a number of catalytic reformers were built. My memory says something like 8, of fair size around the U.S. And that process furnished or produced most of the toluene used for the U.S. manufacture of explosives for World War II. Prior to that, the toluene had come from coal tar, and there just wasn't that much available. So it was very fortuitous that those of us working in the field discovered this, so that we had an almost unlimited supply of toluene. And so cat reforming during the war was really
Janelle,
run.
you have a telephone call on line 2. Janelle, line 2.
Yeah, catalytic hydroforming was run just to make toluene. Following the war, it began to catch on as an octane improver. We were able to make from many naphthas, we were able to make about 85% of 85 motor octane. I remember with the 85. And considering that the raw material for the cat reforming, the native gasoline, had an octane down in the low 50s, you could, it was relatively easy to get a 30 octane number improvement with not too much loss in yield. A large pilot plant was built as Standard Oil part in this consortium in developing the catalytic reforming to make toluene. Then in late in my career at Stanford, Indiana, catalytic cracking was coming on, so I shifted over to catalytic cracking and started to study making catalysts for catalytic cracking. And I did some fundamental research with pure compounds. But Standard didn't want to go too far with that, so they put me over working with powdered catalysts. We didn't call it fluid catalysts those days. It was powdered catalysts. And so nobody knew anything about the fluid properties of slurried powders in gases. So I was put working with the engineers to devise an apparatus to study these properties. And the engineers, the chemical engineers working in the project, had designed this unit, or the feeding device. I was supposed to put the reactor up and the recovery devices. This was going to be run at ambient temperature and atmospheric pressure, just to study the fluid properties of solids and gases. The engineers designed a star feeder, and I had assembled most of my apparatus, and I got to the point where I was waiting on this star feeder to, so that I could, that was their idea of how to control the feeding of this powder. So I hooked up the star feeder and started it up one day, and after about 5 or 10 minutes it ground to a halt. It just couldn't work. It just wouldn't work. And so I called the engineers, and they came and got the star feeder and said, we'll fix it. So there was a hiatus of several weeks, and so I was not doing much, waiting for the star feeder. The star feeder came back, and I hooked it up again and started it up, and it ran a little longer this time, but not over about an hour, less than an hour, and ground to a halt. So they said, okay, we'll take it back. And so I got to thinking, hey, I'd learned a little bit about this flowing these powders around. So I had the idea that, hey, I can make it flow like a liquid. And so I will build me a standpipe and put a tank of catalyst up there, which I'll aerate. And so I built a 30-foot long pipe, something that I made this out of 4-inch or 3-inch glass, Pyrex glass sections. They're 4 feet long. And I just taped them together with tape and hung them on this pilot plant rack, which was convenient, where I had my apparatus. And I started down at the bottom of the 3-inch pipe, I put some taps, which I introduced air and fluidized that material in the pipe. And then up at the top, I had a 55-gallon drum with a whole lot of pipes in at the bottom, with a joint on the bottom that I could connect to the gas. The bottom was flat; it wasn't funnel. I don't remember putting a funnel on that. It wasn't important anyway. But then I aerated the stuff in the barrel also. And then at the bottom of this, I was a pretty good glass blower in those days, so I made a 1-inch, I reduced the 3 inches down to a 1-inch pipe and bent it so it came horizontal, and hooked it up to my apparatus with a rubber hose and with a pinch clamp. So I should put that together and tied the pinch clamp and started to blow air through my system, and then started opening this pinch clamp. And wow, just flowed out of there just beautifully. The more I opened the pinch clamp, the faster. So I was able to study the fluid densities and fluid flow through pipes very handily. And one day, I called the guys up, the engineers who were working on this, and they came down there. 3 of them came down there, and they said, "What are you doing?" So I explained to them just exactly what I was doing. Now, remember, I was extremely naive. I didn't know what was new or what was not new in this. Anyway, three guys started to talk to each other and about this. And all of a sudden they left. And about that time, they decided, when I had a running apparatus, they would take it over. So I was transferred over to some different kind of work, working on isomerization and alkylation at this time. And subsequently, I guess they figured out how to run the fluid catalytic cracking with a standpipe. And the standpipe, as I understand it, became a significant invention as part of the fluid process. I invented it, but I didn't know it. Is that it?
We have run out of time for.
Oh, okay.
We're going to have to